To address the optimal mechanism design problem, we will first look at this problem for a single agent. The reason for this choice is to analyze a much simpler problem to understand the details, and then later we'll generalize it for multiple agents. In this world, there exists only one agent, and we are trying to maximize the revenue that can be extracted from that agent. So what is the setup? We have one typeset. Now there is no subscript because there exists only one player. The typeset is the interval 0 to beta. Now we are going to consider this mechanism f comma p, and f is mapping this typeset into a probability of winning for that object, and the payment will again give a real number. So that's the setup. So with probability, so if f gives a number between 0 and 1, then it is assumed that with certain probability the object will not be sold. Now in this context, the notion of incentive compatibility essentially coincides. The Bayesian and the dominant strategy coincides. So the idea of incentive compatibility is that t times ft, which is the valuation, the expected valuation for player I, for this player, there is only one player, minus the payment that he is making, that is going to be weakly better than when he is misreporting to S. And this should hold for all t and s's. Similarly, individual rationality will mean that this difference, the utility of this player, is always going to be non-negative. So therefore, the expected revenue that the mechanism designer will earn is given by this integral formula. So this is the payment that this player is making, and GT is the probability, and this is the density of the type of this player, G of t. So we are taking the expectation over that type, and at that type t, what is the payment that this player is making? Once you take this integral, that is the total expected revenue that has been earned by the mechanism designer. Now the optimal mechanism design problem reduces to the following. We have to find a mechanism M star in this class of all incentive compatible and individual rational mechanism such that its revenue earned is the maximum, and we'll call this M star to be the optimal mechanism for a single agent. Now the question that we are going to ask in this module is, what is the structure of this optimal mechanism? So let us use this shorthand for f comma p. We denote that with this M, and this is the mechanism that we are going to talk about. Now we already know certain results from the characterization theorem that we have proved before. So we have a characterization result which says that f is going to be monotone non-decreasing. So that is the first condition, and the payment should be given by this expression. So these are the two things that we knew for incentive compatibility. Now from the result on individual rationality, we know that this constant of this Meyerson's integral formula must be non-positive, and that is necessary for individual rationality. Since we want to maximize the total revenue, so we don't really want to have a smaller payment, and it cannot be more than 0. So we are always going to assume that the P0 is always 0. So that simplifies the payment expression even further. So now we don't even have that constant term anymore. We have t of ft minus integral 0 to fx of tx. And we also know that f is monotone non-decreasing. F is non-decreasing. So these are the results that we know from the characterization result. Now in the optimal mechanism, the payment, so after this simplification, we see that even the payment is only dependent on this f. The moment you fix an f, the payment is already fixed, and therefore the optimization problem to find the optimal mechanism is just to find that optimal allocation function f. So the expected revenue, if we just now replace the same expression, we plug the value of P of t into this expression, then we get this expression, and this is the expected revenue under this mechanism F, and we want to maximize this with respect to an F which is non-decreasing. That is the requirement for incentive compatibility. Now we have this small lemma here which says that you can simplify this expected revenue. There are two integrals here, but you can replace it with one integral and say that this expression reduces to this form where you have gt here. Actually there is something missing out here, so there should be one ft also, ft multiplied, and so this will be gt multiplied by ft and then multiplied by this expression, which is often denoted by w of t and also called the virtual valuation. So the reason for this virtual valuation is pretty simple. If you had only t, it was the real valuation, but now we are actually subtracting out some expression which is dependent on the priors, and that is why it is called the virtual valuation. So that is the w of t. So you can actually write this expression as integral 0 to beta wt times ft and gt. So that is the reduced expression. So let us now look at the proof. It is essentially pretty simple. So this is the original expression that we have derived just by substituting the value of p. Now once we have that value, we can just distribute this, and the first term remains as it is. The second term, we have two terms. One is the integral with respect to this x, which is the inner integral from 0 to t, and then that is integrated with this expression gt times dt, and that is integrated from 0 to beta. Now what we are going to do is a standard limit switching between these two expressions. So what we want to integrate, we want to push this integral, the inner integral later, and the outer integral we want to do it earlier. So let us look at the limits. So we have two variables here. One is x and another is t. And in the original integral, we were having this x varying from 0 to t. So this is the t equal to x line here. So we were first taking from 0 to this value of t for this value of x, and then t was being moved from in this direction from 0 to beta, right? So in that sense, it was essentially sweeping this whole space, the upper triangular space. Now we are going to do the integral, but in a different way. Now we are first iterating over t. So t goes from this value x to the value of beta, and then x takes values from 0 to beta. So that is essentially what we have done. So now we are integrating with respect to t first, going from x to beta, and then we are going from 0 to beta for that x. So we are just exchange this order of this integration. Okay, so that means that now we are in a situation where we can, so t and x were just some running variables. We can also switch them and write this. So here, which was t, now we have written that as x, and x becomes t now. So by that replacement, what we can do here is that we see that integral of g of t, small g of t, because that is the density, it turns out to be the capital G of t. And because at beta the distribution is limited between 0 to beta, so therefore at beta the value of capital G is 1, and minus that with g of t. So this inner integral just reduces to 1 minus gt, and the rest of the thing has ft here. So now we are in a good shape, because the integrals, both of these integrals have the same limit. So we can essentially merge these two pieces of these integrals and write it in a compact form: t minus 1 minus capital G of t divided by small g of t, and now you have gt times ft, and that is exactly what we wanted to show in the beginning. Alright, so that lemma gives us a much simpler form, a compact form of the expected revenue. Now the optimal mechanism's job is to find the maxima of this, subject to the condition that f is non-decreasing. That is a necessary condition for this mechanism to be incentive compatible. Now we are also going to assume one other property. I mean, this in general might be quite difficult to solve, but we are going to assume some regulatory property of the distribution G, which is called the monotone hazard rate condition. The property says that g of x, the small g of x, by 1 minus g of x, so that is just the inverse of this term, is non-decreasing in x. So this is not a very restrictive assumption, because there are certain standard distributions like this uniform distribution and the exponential distribution which satisfies the MHR condition. Now so why did we actually assume this? What are the implications of this result? The fact that we can show is, if we have a function, a g function, which satisfies this monotone hazard rate condition, then you can actually have a unique solution to this expression. So x minus x equal to 1 minus g of x times the small g of x, that has an unique solution. And this is not very difficult to see. We know that 1 minus gx, so because gx by 1 minus capital G of x is monotone non-decreasing, that means that 1 minus capital G of x divided by small g of x is monotone non-increasing. So that will look something like this, this curve here. And we also know that x is a monotone increasing function. So these two curves can intersect exactly at one point, and there is a unique solution. It will definitely intersect, and it will intersect exactly at one point. So that is the point we are going to denote with x star. And now if you look at this virtual valuation, which we have said earlier, x minus this expression, so this expression, this value is going to be 0 at x star. So wx star is going to be equal to 0. And we have also seen that when you look at this expression, so we know that gx by 1 minus capital Gx is monotone non-decreasing, so inverse of that is monotone non-increasing, and therefore minus of that is monotone non-decreasing again. And x is anyway increasing, so therefore w of x together is an increasing function. So in some sense, if you plot that, wx will always keep on increasing, and we know that at x star it is actually hitting this 0 point. So any value which is when x is smaller than x star, the value of w of x will be negative, and anything larger than that, it is going to be positive. So that is a very important observation. This the virtual valuation is flipping its sign at this point x equal to x star. Now if you look at the this expression, the optimization problem, so notice that this is nothing but w of t, and all that we will have to design for this optimal mechanism is to find out what is the value of f of t. Now I know that wt is going to be 0 at x star, and anything smaller than x star it is going to be negative. Anything larger than x star, it is going to be positive. Then in order to maximize this sum, if you did not have any such constraint like this non-decreasingness, what should you have done? Quite clearly, when t is smaller than x star, you should not have allocated this object. This object would have given you negative expected revenue. So you should not sell this object when this is happening, and sell this object when it is greater than x star. And at the point of x star, you can do anything. You can pick it. You can cell with any probability between 0 and 1. That does not matter. So therefore, the unrestricted solution of optimization problem 1 is the following, is the one that we have just discussed. But quite interestingly, this unrestricted problem is actually non-decreasing. You can see that. I mean, what you are having, so f of t, if you like to plot it, as you increase t at x star, before x star you are not allocating it. At x star you start allocating it, and at this point you can have any value. So the ft can take any value between 0 and 1, but for all those values it is monotone, non-decreasing. So therefore it is an optimal solution for optimization problem 1. So we have actually solved this problem of finding the optimal mechanism for a single agent, and under the assumption that this G satisfies this monotone hazard rate condition. So therefore we can summarize all the findings, all the discussions in this module into this theorem. The mechanism F comma P under the MHR condition is optimal if and only if these two conditions hold. Of course, this is in one direction, but you can, the other direction is quite obvious. The other direction is quite simple. So F is given by this equation 1, the one that we have already discussed, and then you have the payment formula. So if you just apply the rule, the Meyerson's payment formula that we have already discussed here. So the payment expression was given by this integral formula. You will find that whenever you have a type which is larger than x star, then you are extracting this payment of x star, and when it is smaller than that, you are not selling that object, and also charging a payment of 0. So this mechanism is so this is the characterization result for the single object, but for only one player. In the next module we are going to generalize it for multiple players.